presently is technical leader of the flammability team at Factual Mutual Global. His current interests is in the pyrolysis modeling and optimization algorithms, as well as application of advanced experimental techniques and diagnostics to flammability testing.
Thank you. I would like to inform the speakers that the time for presentation is 20 minutes. In order to control the time for presentation, a green card will keep on the table indicating that you are on time. When there are 2 minutes remaining, a yellow card will be placed on the table. The placing of a red card means that the time has ended, so you should finish the presentation today.
Well, thank you. Thank you everybody for coming. Thank you, Professor Lina, for the introduction. I'm going to be talking about a subject that's been an area of research for the last several years, maybe 2-3 years. And basically I want to bring an update of what has happened since the first time that we presented this work. But let me start by putting this in the framework of a larger context. At FM Global, we're interested in developing a computer simulation tool that can allow us to have predictive capabilities that can be applied to large-scale fires. Not only fire growth, but also fire suppression. And this is something that where we're at right now, where we've coupled fluid dynamics combustion with water suppression. Somehow, this is somewhat qualitative, but it kind of gives you the state at which we're in right now in terms of prediction of fire dynamics. This is basically a simulation of a reduced array. It's 4x2x3 boxes that are about 1 meter cube. And we're putting on a uniform flux of this 0.3 gallons per meter per foot square. It's about 12 liters per minute per meter square. And as you can see, qualitatively, we're able to predict the reduction in fires as we start applying water. Granted, this is a pretty large flow rate. And down on the bottom, you have a number of publications in the last 2 years that kind of like lead up to this work. So we have, as I said, interest in modeling fire growth and having a tool that can be applied to large-scale modeling. Because as of now, all our fire protection requirements and standards are developed through the use of, or through the experimentation with large-scale testing. And as you can imagine, that large-scale testing comes with a large cost. So having a modeling tool that is predictive and has predictive capabilities can allow us to cut down on the amount of large-scale testing that is needed, and also thus reducing costs, and also allow us to have a tool that where we can interpret experimental results better, we can extrapolate, we can interpolate, and so on. So it gives us much more flexibility. As of now, we're interested in corrugated cardboard. Cardboard is a material that can be found in every warehouse setting, every warehouse scenario. So it is important for us to understand the flammability and fire hazard characteristics. So that's one of the areas of research that we're pretty involved in. And that's some of the work that I'm going to be presenting here today, which is related basically with vertical fire spread and fire growth over corrugated cardboard panels. As I said at the beginning, this is something that we've worked on already. We've presented some results, but we've advanced the model since that time, and that's basically what I want to present here today. Initially, when we did the simulations, the agreement was okay. There were some discrepancies that remain, and those are the ones I'm going to be addressing today. Okay, so what I'm going to be talking about is basically these modeling upgrades or extensions that we've done since we originally developed the model, which are basically applied to the gas phase combustion, some subgrid scale turbulence near the wall, also charge sedation, and also some upgrades on how we determine material properties to the solid phase pyrolysis model and in the overall scheme. And then we're gonna put everything together and run again the simulations of the parallel panel case and compare with experimental data. The experiment in question is this parallel panel. Basically consists of two panels that are about almost 2.5 meters tall, and at the bottom we have a 0.3 by 0.6 sand burner that is putting out a source fire of 60 kilowatts. So it's a propane burner, and this is actually a standard test at FN Global to determine the flammability characteristics of semiconductor materials. In the semiconductor industry, you cannot have sprinklers for obvious reasons. So all materials that go into a clean room, for example, have to have the ability to not spread fire. So this is a test that we do to determine that. So we've used this, in addition to being a standard test, it's also, from a modeling standpoint, is attractive because it's geometrically relatively simple. So you can actually generate a grid for this relatively easy. As opposed to the standard test itself, we've instrumented these panels quite heavily. As you can see here, these are all heat flux, so we have heat flux along the center of one panel. We have thermocouples to measure surface temperature along the center line and offset of the other panel. And this is the actual point data that we'll use as partial validation of the model results. In addition to this, we also measure heat release rate as the fire propagates over the material. All right, this is a picture of the parallel panel action. So for the numerical modeling, we use a open source tool that we developed in-house. You can find the model itself at this address. It's a large area simulation solver based on the CFD toolbox offered by OpenFOAM. And we have added several subgrid scale models. The subgrid scale turbulence is treated via eddy viscosity in a gradient diffusion model. Soot formation, oxidation, radiation, it's treated with the laminar smoke point based model, which Professor Delitacios alluded to earlier. And then as far as the solid phase pyrolysis, we're using a simplified one-dimensional model with one-step reaction that turns the virgin material to gas and char, and it's a final rate, a Regent's type rate. And for this type of model, since it is not a detailed, comprehensive model, we have an approach to actually determine the material properties that go into the model. We call it effective, model effective or model specific material properties. Okay, as far as the extensions, we have 4 listed here. What I'm calling this whale is a wall adapting local eddy diffusivity model. As you can imagine, for large scale models, we lose a lot of resolution if we want to treat a large domain. So near the wall, we lose a lot of information, especially transition to turbulence, boundary layer, and so on. That cannot be treated with the model assets with the resolution that we have right now. So we've come up with the subgrid scale model that can represent the phenomena that happens near the wall. Especially, this is very important for us in order to determine the convective fluxes of the wall, which with our previous model were completely over-predicted, and I'll show some of that. Also, we have the combustion model is based on the eddy dissipation concept. We used to employ the mixture fraction for this model. We've extended this to have several species treated, especially since we're interested in doing suppression now. So now we treat the fuel oxidizer, CO2, and water. But as you can see, these two are in italics. I'm not going to be talking much about those, basically due to time. These are subjects that can, be hours all in itself. So I'm going to be centering in what we've done with char oxidation, which wasn't treated previously, and also the boundary conditions as we employ this material property estimation algorithm that I'll be describing. So for char oxidation, it's very clear at the moment, very, very simple. But basically, we're doing this to try to see what the effect is of having char oxidation versus not having. So the way we're treating this is saying, okay, the heat combustion contained in the virgin material which we can determine via a bomb calorimeter experiment, can be expressed as the mass fraction of volatiles that escape during pyrolysis times the heat of combustion of pyrolysis, and then the mass fraction of char that is left behind times the heat of combustion of char. And the heat of combustion of char, at this point, we're treating it as the heat of formation of CO2 per unit mass of carbon. So we're assuming that the char left behind is mainly composed of graphite or carbon. And when it oxidizes, it just releases CO2 with this heat of combustion, which is relatively well known. So from that, we then can calculate what the heat release rate per unit area is due to char combustion, which is the formation rate, the mass formation rate per unit area of char times the heat of combustion. And then this rate is approximated by this expression here. This is basically the mass diffusion of oxygen to the surface divided by the stoichiometric mass ratio of this reaction. And this is the char mass fraction per unit surface area, char mass, by the time resolution. So basically, and then there's the char mass fraction is the integral of all char available in the material minus what has already been formed. So basically, what this approach does is to consider the char formation and oxidation process as strictly a surface reaction. And the char oxidation is also a surface reaction that is determined or driven exclusively by the mass oxygen diffusion to the surface. So as I said, it's relatively simple. This assumption, actually, we've confirmed this by doing oxidative pyrolysis experiments, and that has been published in the combustion symposium earlier this year. And also another assumption is that the bulk properties of material must substantially change once you have the char oxidation reaction. And this is just to simplify implementation in the model. Again, relatively crude, but our intention is just to see what is the difference in the actual large-scale simulation when we have this versus when we don't. All right, for the material properties, this is basically it in a nutshell. We have a bench scale experiment from which we're measuring some observables. We have an input to it and then a response. I'm differentiating here between true input and true response versus what we observe in order to represent that all these measurements have some inherent uncertainty to them. And then we use a model to represent what is observed from the bench scale experiment that is subject to some input parameters, and then we adjust these parameters through optimization so that the model response matches the experimental observation. So that's basically the optimization approach that we're doing. And of course, in the context of the present application, we are interested in getting material properties for the pyrolysis model. And of course, these parameters are going to be the so-called material properties. And this is something that was published a couple of years ago, again, in the combustion symposium. The bench scale experiment that we're talking about here is the results that are obtained in a fire propagation apparatus, which is schematically shown here. Basically, we have a sample that is sitting on a load cell, it's being weighed as it receives external heat flux at various levels. And basically, the two observables that we're interested in these tests are the mass loss rate and also the surface temperature that is measured with an infrared barometer. Again, the material in question that we're interested in is corrugated cardboard. So it is a hygroscopic material. We need to control the relative humidity, which we're able to do in our system. We're able to control the relative humidity of the air, of the environment that this material sits in. For all these tests, we use 100 nitrogen as the environment. So they were all extremely pyrolysis, no oxidation. Okay? And we're using an insulated sample holder that can give us a well-defined boundary condition on the back of the sample. But what I want to talk about also for the pyrolysis model, obviously the pyrolysis model is very sensitive to the boundary conditions that you employ, right? And I mentioned the insulation on the back that gives you some type of well-defined back boundary, but what happens at the front also needs to be determined because between a fire scenario and the FPA scenario, we have a very different spectral environment. So as I will show, the FPA heaters operate at a relatively high temperature, which is much higher than what you would encounter in an actual fire scenario. So we actually need to determine, to characterize the heaters and how that radiation interacts with the surface of the material. So there are two experiments here that we're going to be doing. One is to get the spectrum of radiation from the heaters as a function of heat flux, measure with this spectrometer, it's a dispersive line-of-sight spectrometer. Basically breaks up the incoming radiation with a couple of prisms and directs it into a lead selenide detector that operates between 1 and 4.5, 5 microns. And then we're going to be also measuring surface emissivity of the material by using two instruments. One is ultraviolet visible and near infrared, basically from about 250 nanometers to about 2.5 microns wavelength. And then also an FTIR that works from about 2 microns to about 20 microns. And we use an integrating sphere to do this. So basically, we measure the reflectivity of the sample versus a calibrated reference and employ Kirchhoff's law by assuming the material is completely opaque. So 1 minus the reflectivity is the emissivity. And we do this as a function of wavelength. All right, so let's go on to some results. This is the heater output. And this is some curves versus applied heat flux. And as you can see, I'm putting here the data and the lines. I don't know if you can see the color, it's pretty not that good. But anyway, take my word for it. The lines are pretty good. And basically, this is just a Planck's radiation distribution with a assumed emissivity or a fitted emissivity. The emissivity comes out to be relatively low, 0.1. Let's keep in mind that these radiant heaters are tungsten halogen. Tungsten, the emissivity is actually pretty low, and I'm making reference here to looking at the width. They actually record emissivity values for tungsten that are consistent with this value up here. But what I want to show here is that actually the radiation is gray body light. If you actually take this intensities and divide it by t to the fifth, if this is a gray body, all those curves will collapse into one curve. This is what I'm doing here. And this is a relatively good collapse, not so much along the wavelength, and this is because of emissivity changes as a function of wavelength for tungsten, as well as interaction with quartz. These heaters have a quartz window and also the tungsten excitation quartz, and you see some of that effect along the wavelength. But for the most part, they're relatively well represented by a gray body distribution. And just lastly, we have here column temperature as a function of heat flux is a power curve, and this is consistent with actually what the manufacturer of the lamps gave us, so it's a good double check. As far as the emissivity, this is a little bit shown differently. I'm plotting here versus wave number so that the near infrared and the visible can be expanded. The line is what we measure for corrugated cardboard. And what I'm showing here, which is actually pretty interesting, and we're still looking at this, is that if you look at similar cellulosic materials, there was some data at SP in Sweden, they measured plywood, oak, and some other woods. They're nearly identical to cardboard for beyond 1.5 microns. And this is I'm guessing here is basically due to the nature of the material themselves. They're all cellulosic materials, so this is actually to be expected. They're actually essentially the same long wavelengths, and the near infrared and visible wavelengths are different, and this just due to a difference in color. That's all this saying. But we're going to use this curve for the emissivity, and the curves for the emission, and use this equation to get the effective emissivity of the sample, and then for the fire case, we're going to assume that the flame temperature is around 1400 K, and then do the same here. So basically, our intensity goes to a quartz glass, so there's a transmissivity times intensity, and it falls on the surface, and whatever is absorbed is actually the emissivity times the transmissivity times the intensity. So when we do this integral, that gives us the effective emissivity. So we applied this to all the heat flux levels that we used in the experiment, and also for the fire pace. And as you can see, there's actually quite a bit of difference on the calculated emissivities versus the fire pace. So this is what we will use in the model. This is what in the full-scale model. This is what we use in the pyrolysis model, in the optimization code to get our properties. Okay, so this is what it looks like. I'm just showing one case for 60 kilowatts per meter squared. The other cases are equally as good in terms of the agreement. This is what we had before when we first did this, where we actually left the emissivity be a variable parameter, and this is what we're getting now. They are different. We're getting similar agreement with the experiment. Basically, these three parameters and the emissivity are coupled through an effective thermal inertia. So when you fix this, all the other parameters are going to vary. Okay, let me just move on. I'll spend too much here. So the full simulation for the parallel panels, this is the domain. We're going to simulate a 3x3 by 8 meter domain. We've used an adaptive grid and have most of the refinement between the panels and along the burner. So it's about 70% of the cells are concentrated in this region. And this is how it looks like. Okay, so this is our first attempt. And basically this is shifted because we were, one, over-predicting the convective heat transfer on the panels. Also the peak is low. We weren't using char oxidation. Peak is low basically because the emissivity is low, so everything bounces around and just leaves. So once we integrate all the modifications that I explained earlier, this is the curve that we get. And of course now we're over-predicting the peak quite a bit. But once we start using char oxidation, the char oxidation approach that I showed you, we're reducing the peak, then we're widening the curve, which is what we expect, and the fire growth is actually captured pretty well. This simulation is actually the simulation for this curve. So you can see that it dies down quite rapidly. Okay, and pretty much out of time, let me just switch. These are some curves for the heat flux along the panel. If we go up on the panels, we go like this. Again, fairly good agreement. This drop is due to the passage of the flame. If you have questions, just ask me at the end. I can talk about that. So just to summarize and conclude, we've improved our original parallel panel simulations by including some upgrades like char oxidation, wall phenomena, and an updated approach to the material properties. Those ensure that our properties are transferable to the actual large-scale scenario by modifying this emissivity issue. And our global data and local data are actually going to be reduced by using this approach. Okay, there's a lot of stuff that we're working on. Does this apply to other materials? How does it scale? What happens once we are in a big fire? We can no longer assume this is all we think. We need to go to a big scenario and a lot more. So let me just acknowledge my colleagues out from Global, and thank you for your time.
Thank you very much for your presentation. And now the session is open for discussion. There are some. Yes.
It's an excellent work. I know a bit more. And what I would like to understand, I didn't understand something. Does the emissivity change as the surface changes?
Yes.
It was not clear.
Yeah. I'm sorry. That only referred all the emissivity values that I was talking about. That only refers to the virgin material. Now, for the char, I didn't show, but the char spectral distribution of emissivity is essentially flat. So you can just assume a constant.
One.
Near one, it's about 0.9. So that's all for virgin material. Yeah, char is a constant.
But also, when it spreads upward, there is shoot deposition.
Yeah, we don't treat that. No. But for most of the heat fluxes that you see in fires, the surface turns to char very rapidly. So the effect of soot deposition is probably minimal.
Yes.
I think in that paper from SP that you mentioned, they found that if I remember well, the emissivity of the char, the blackened wood, is actually lower
Yes.
than the virgin material, which is kind of counter to what everybody has thought.
Yes.
Do you find, I mean, what do your measurements show as far as the emissivity of the charred material versus the virgin?
Yeah, it does. Let me go back to that. Okay. So once you start charring, this line starts going up, and this line, this portion of the line actually goes down a little bit. Okay, so on an integrated basis, if you don't consider this, just consider this region, the char emissivity will be lower, yes. But for our purposes in the FBA radiation is concentrated here. So this is going to have a huge effect on the actual results. Yeah, the char emissivity does go down, but it's only in this region. Yeah. But still, for a thing that I think it goes 0.85 or something like that.
Capture very much.